We've been doing mole problems as really the first step of what is called stoichiometry. When you're baking cookies or cake or some other item, a recipe is often used, telling you the exact amounts for each ingredient and, of course, how much it is that you would like to make. If you need to make more, for instance, double the recipe, make twice the cookies, then you need twice the ingredients. In other words, there's kind of a ratio between what you need and how much you want to make. Well, chemical equations are the recipes for chemical reactions. Here's a reaction. We have methane, O2, oxygen, CO2, carbon dioxide, and water. In this reaction, there are two molecules of benzene, that's the C6H6, reacting with 15 molecules of oxygen to produce 12 molecules of carbon dioxide and 6 molecules of water. Or you can think of it all as being in moles. In other words, it's 2 moles of the benzene reacting with 15 moles of oxygen to produce 12 moles of carbon dioxide and 6 moles of water. Those numbers that are in front, those coefficients, tell us basically how much of the things we need in our recipe. It's just that they're all done in moles as opposed to cups or ounces or, how many eggs or something. 2 moles of this, 15 moles of that. If I only wanted to make 6 moles of CO2, notice that there's a 12 in front of the CO2, but I only want to make 6, well then I'm only going to need half of my recipe. I'm only going to need 1 mole of the C6H6, 1 out of the 2, and I'm only going to need 7.5 moles of the O2 as opposed to the 15 because I only want to make half. As long as the mole ratios are maintained, the chemical reaction recipe will determine how much product will be produced and how much of the reactants, the ingredients, are needed. And when we say mole ratio, notice that when I said I want 6 moles of CO2, okay, the equation has 12. 12 is, of course, 2 times 6. In other words, the CO2 is 6 times bigger than the C6H6. Well, if I only want 6 of the CO2, I still need to be 6 times bigger. Well, 6 is 6 times bigger than 1. I could go to a quarter recipe even. I mean, it doesn't have to be any nice number. And therefore, if I only wanted to make 3 moles of CO2, well, then I'm just going to need half a mole of the C6H6 because, again, half times 6 gives me 3. I'm maintaining those mole ratios. Now, there are some conservations of matter when you look at a chemical reaction. When we were figuring out our balanced equations, in other words, the 1, the 3, and 2, which are mole ratios between the different items in the equation, we, of course, did that to make sure that the number of atoms matched on both sides of the equation. So that 1 in front of the N2 means there's 2 nitrogen atoms on the left. That 2 in front of the NH3 makes sure there are 2 nitrogens on the right. So there's 2 on the left, 2 on the right. Likewise, the 3 in front of the H2 gives us 6 hydrogen atoms on the left. The 2 in front of the NH3 also gives us 6 hydrogen atoms on the right. The only difference is things have been rearranged, but every atom is accounted for, and that's what we were doing in balanced equations. Now, it turns out the same thing is true when you look at mass. Okay, it has to balance there. You can't lose mass. You can't gain any extra. You can just rearrange what's there. Well, if I go to the periodic table and look up N2, nitrogen's Mass is 14 for 1 mole. I have N2, so that's 28. Hydrogen is number 1, of course, so it's 1 gram. H2, therefore, would be 2 grams. 3 times 2 is 6. 28 and 6, that's 34 grams. Likewise, NH3, 1 nitrogen, 3 hydrogens, that's 17. I have a 2 in front. 2 times that 17, that's also 34 grams. So I have conserved my mass on both sides of the arrow. Everything has to go somewhere. They've just been rearranged as to where they fit in. Stoichiometry allows you to find out how much of any substance that you need, as long as you know what the equation is, it's already balanced, and you know one substance, other substance in the equation. In other words, if I know what the oxygen amount is in this equation, then I can figure out how much CO2 I'm going to produce, how much H2O I'm going to produce, or how much C6H6 I need in order to use up that amount of O2. Now, there are basically 3 steps to stoichiometry to do a stoichiometry problem. The first is what I call go to moles. We need to determine the number of moles. Well, we've been practicing for a week now mole problems, and that's essentially step 1. We don't measure things in moles. We're going to measure them in grams, just like you did with the chalk, okay? Or in the lab last week with the salt and the sugar. We measure out grams. But then we have to look at the molar mass, the gram formula mass, add up all the atoms that are in that formula to figure out its molar mass for 1 mole. Then we can convert the grams into moles. Now, if it's a gas and we have it in liters, well, then that's a 22.4 is what we used, and we went over that last time. Or if it's in atoms or molecules, formula units, then we use the mole number, the 6 times 10 to the 23rd. So step 1 is just go to moles. Step 2 is really the new part for our stoichiometry. That's where we have to use the equation, the recipe, to come up with the proper mole ratio. And then step 3 is really another mole problem. It's just that this time we know how many moles we've got, and we want to change it back into either grams or liters, molecules, atoms, and so forth. So we've really been doing steps 1 and 3 already. In fact, sometimes we did both steps 1 and 3 in the same problem when we changed, say, from grams to liters. The difference here is we're going to have a step 2 with the mole ratio, and we can figure out about a different substance where all the mole problems we were doing so far just involved one substance at a time. So we're going to go over the 3 basic types of stoichiometry problems, and the first is called the mole-mole problem. And the nice thing about the mole-mole problem is there's really only one step to it, just step 2. Because if we, again, think step 1, go to moles, a mole-mole problem is I'm already in moles. That's the information I was given. And step 3 is to go from moles to grams or liters or molecules, but the problem just wants you to have an answer of moles, so I don't need to do step 3. All I need to do is step 2. So, for example, how many moles of CO2 are produced if 5 moles of O2 are used up? So what I do is, just like in all our mole problems, I write down the number they gave us and its unit, the 5 moles, and then I'm going to multiply that times the mole ratio. In this case, that's the 12 over 15. Now, how do I get the mole ratio? Well, the mole ratio is basically what I don't know, the question mark, divided by what I already know. Well, what's the question mark in this problem? It's the CO2. That's what I don't know. So that's where the 12 comes from. The 12 is in front of the CO2 in the equation. Where'd the 15 come from? Well, that's the number in front of the O2. In other words, it relates in my equation the CO2 to the O2. The question mark is always the part on top. And it would really help when you're doing these problems if you go ahead and make a little note just the way you see I have here on the screen. In other words, I look at my question and I go ahead and I put the question mark. That's what I want to find out about. In this case, the CO2. And I take, oh, that's what I've already been told, and I put that underneath where it shows up. That way, I know what my mole ratio is. Question mark over what I already know. 12 over 15. And then it's just a matter of do the one step. The 5 can cancel with the 15. Basically, I end up having 12 over 3. Answer is I'm going to produce 4 moles of CO2. Note, okay, that if I looked at 15 over 12 as a fraction, 15 over 12, and reduced, it would be 5 to 4. So the ratios always have to be maintained. That's the purpose of our equation. It tells you how everything in the equation relates to everything else. And again, the mole ratio is what's unknown, the question mark, over what I already know. And we use the numbers, the coefficients out front to do that mole ratio. So, another example. How many moles of O2 are needed to burn 6 moles of C6H6? Again, put the question mark under the O2, put the 6 moles under the C6H6. That's what I want to find out here. That's what I already know. So my mole ratio is 15 over 2. Put down the 6 moles I've already know times 15 over 2. Again, a little bit of canceling. I need 45 moles of O2 to be able to use up 6 moles of the C6H6. Please note the same equation I had before, it's a different mole ratio because it's a different question about that equation. In other words, this time it's the O2 I want to know about, not the CO2. And this time I'm told about the C6H6. And so I have a different mole ratio. All right, and then finally, another last example here. How many moles of H2O are produced when 3 moles of CO2 are also produced? See, it doesn't matter. I don't have to be on one side of the arrow or the other. They both can be over here. If I know one of them, I use the mole ratios to find any of the others. So in this case, question mark under the H2O, that's what I want to find out. So I'm going to have a 6 on top. The 3 moles I wrote down underneath the CO2. This tells me my mole ratio, 6 over 12. Unknown, the question mark, over known. So 3 times 6 over 12, 3 times 1/2, 1.5 moles of H2O. So those are mole problems. One step, pretty simple. Now it turns out that volume problems, which means I start in liters and I'm going to end up in liters, I can do the same way with one step. Now, technically, I can do them in 3 steps too. I can take the liters and then divide by 22.4, make it moles, do my mole ratio, second step, and then in step 3, take the moles and multiply by 22.4 liters to turn it back into liters. But that just means step 3 undid what step 1 did. Divide by 22.4 and then turn right around and multiply by 22.4. Why do the extra work? So we can just take a shortcut and just do step 2, the mole ratio. So how many liters of CO2 are produced if 5 liters of O2 are used? Okay, put down my 5 liters times, again, 12 over 15, 4 liters. And in fact, if we go back just a moment, look how this is basically the same problem we just did. It's just instead of moles, 5 moles of O2, 12, 15, 4 moles of CO2. This one's done in liters. Same problem, it's just done in liters. And again, the mole ratio, what I don't know, the question mark, over what I do know already. In this case, I then use 12 over 15 for my mole ratio. Again, volume problems don't have to convert liters to moles, since step 1 divides by 22.4 and then step 3 multiplies by 22.4. 22.4 over 22.4 is just 1. So, a couple more examples real quick. How many liters of H2 are needed to produce 10 liters of NH3? Question mark. How many liters of H2? So there's my question mark. So the 3 is going to go on top. Here's what I already know. The NH3, 10 liters of that. So 10 liters times 3 over 2. 15 liters of H2 will be needed. Okay, in this case, how many liters of NH3 are produced when 4.5 liters of H2 are used? Question mark's over here now. 4.5 liters is over here. My mole ratio is 2 over 3. 4.5 times 2 over 3 is 3 liters. What I want you to notice is in this one, it was 3 over 2. In that one, it's 2 over 3. How am I supposed to keep it straight? By going back to the definition of mole ratio. Put that question mark down. Put what you already know down. That'll tell you the order. Question mark's always on top. So up in this problem, it's 3 over 2. Down here, it's the NH3 I want to know. That's what I don't know already. That's the question mark. So this one is 2 over 3. Now, for mass problems, or for that matter, mixed problems, when I'm going, say, from grams to liters, or going from molecules to grams, anything that's not the same, in that case, I have to do all 3 steps. I have to first go to moles. So, just like in the previous problems, I look at my question, how many grams of CO2? Put that question mark under the CO2, little note to myself, are produced if 320 grams of O2 are used. There's my 320 grams of O2. So my mole ratio, right off the bat, even though I'm not there yet, I know it's going to be 12 over 15, the question mark part over what I already know. So step 1, go to moles. Right here. That's a basic mole problem that we've been doing the last week. I take my grams times 1 mole over the 32 grams. Where'd the 32 come from? Well, this is O2. Oxygen has a mass of 16. I have 2 of them. 2 times 16 is 32. 320 divided by the 32 gives me 10 moles. Okay, now, mole ratio. Do the 2 that the 10 moles that I just figured out in step 1, and I'm going to go times the 12 over 15. Again, the question mark over the 15, the 320 I already knew. There's my mole ratio. Can do some canceling. 10 and the 15, 2/3 times the 12 is 8 moles. So there's my step 2. And then I don't want to know moles in this case. I want to know grams. So this would be another one of my mole problems that we've been doing, where I already know the moles, and I go times 44 over 1 mole to give me my answer in grams, 352 grams of CO2. So we've already been doing step 1. We've already been doing step 3. It's step 2 is the new part, and the step 2 uses the equation to tell us it's our recipe. Also, just as a reminder, hey, when I want to know moles, when the question is how many moles, notice that it's 1 mole over the molar mass, the gram formula mass of whatever substance I'm looking at. When I already know the moles, then it's the grams over the 1 mole. So step 1 is always divide. Step 3 is always multiply. Okay, we've already been doing 1 and 3. We're just putting them together in one problem. Okay, another example. How many grams of NO, there's my question mark, are produced if 24 grams of O2 is combined with excess ammonia. Anytime you see the word excess in one of these questions, it just means I have all the ammonia I need to use up all of the O2 that I want to, in this case, transform into these products. So step one, go to moles. 24 grams times 1 mole over 32 grams gives me 0.75 moles. Okay, take that answer. Step two, times the mole ratio. All right, 4/5. Where did the 4/5 come from? My equation, question mark on top. The 4 over the 5, the thing I already knew. That gave me 0.6 moles of NO will be produced. But I want to know how many grams will be produced. So I go to grams, 0.6 times 30 grams. Where's the 30 from? Look at the periodic table. 14 for nitrogen, 16 for oxygen, 14 and 16 is 30. So 30 grams per mole, 18 grams is what I'm going to produce. Another example. How many grams of Al2O3, aluminum oxide, are produced if 36 grams of aluminum is combined with excess oxygen? So now I'm looking at the aluminum. Question mark over here, 36 grams over there, my mole ratio, 2/4. This one is written a little bit differently than the last one. Instead of doing 3 separate steps, I've now made it one long problem, but here are the 3 steps right there in blue. That's my step 1. I'm changing the grams. The grams will cancel. I'll have moles. Right here in red, that's my mole ratio. There's my step 2. And then over here, as a final step, is my step 3, where I'm changing that answer back into grams to get my 68 grams at the end. Again, the 102 comes from adding up 2 aluminums and 3 oxygens. So sometimes you'll see it written as one long problem where it's still step 1, go to moles, step 2, mole ratio, and step 3, go to whatever the desired units are. And as I said, this would also be true for mixed problems. In other words, I could start at grams and do just what you see here, but let's suppose that I wanted to go to liters and not grams at the end. Well, then this one would have been use 22.4 because that's our number for liters. Oh, what if I want formula units? Well, then up here, instead of the 102, I would again just use the mole number, 6 times 10 to the 23rd. Grams, got to look it up. 22.4 if I want liters, and 6 times 10 to the 23rd if I want molecules, atoms, or formula units. But it's still going to be go to moles, step 1, mole ratio, step 2, and in this case, I went to grams for step 3. So those are the kind of problems that you'll be expected to do, on the next test. It won't be until after the break, but essentially, you got to be able to do mole problems. You got to be able to find the molar mass of something, and then you got to be able to use the equation to do things. And of course, we can't do any of this unless we actually had a balanced equation. So, in the scheme of things, when we were balancing equations, that was doing part of stoichiometry as well. Recipes wouldn't be very good recipes if you didn't actually know how much of each ingredient you were supposed to use. Because I can tell you right now, salt and sugar in equal amounts do not work.